Hello once again. Last time we were able to solve simple systems of linear equation in two variables using the basic method of elimination by addition. And we also demonstrated how we can solve by elimination by converting this system into a row echelon form. In continuation, we will be solving the system of linear equation using an algorithm called Gaussian and Gauss-Jordan elimination. Now, what are the objectives for the day? First, you must be able to determine the size of a matrix and write an augmented or coefficient matrix from a system of linear equation. You should use matrices and Gaussian elimination with back substitution to solve a system of linear equations. You also should use matrices and Gauss-Jordan elimination to solve a system of linear equations. And you should be able to solve a homogeneous system of linear equation. First, we will have matrices. Now, what is a matrix? If m and n are positive integers, then an m by n matrix is simply a rectangular array that consists of rows and columns, and in which entry a sub ij of the matrix is a number. Notice that in a matrix, each element is positioned according to its row number as well as its column number. So for example, we will see that this element a sub 13 is located in first row and third column. So similarly, an element in the last row and last column is given by a sub mn. The entry a sub ij is located in the ith row and the jth column. The index I is called the row subscript because it identifies the row in which the entry lies, and the index j is called the column subscript because it identifies the column in which the entry lies. Now, a matrix with m rows and n columns is of size m by n. So when m is equal to n, that means we have equal number of rows and columns. The matrix is said to be a square matrix of order n. And the entries A11, A22, A33, up to A sub nn are the main diagonal entries. For example, let us identify the size of the matrix. So each matrix has the indicated size. So if you only have one entry, so the matrix has a size of 1 by 1, and letter B is 2 by 2, and letter C is a 2 by 3 matrix. The matrix derived from the coefficients and constant terms of a system of linear equation is the augmented matrix of the system. The matrix containing only the coefficients of the system is the coefficient matrix of the system. Say, for example, we're given a 3 equation in 3 variable system. So we have here x minus 4y plus 3z is equal to 5. Negative x plus 3y minus z is equal to negative 3. You have 2x minus 4z is equal to 6. The augmented form of the matrix of this particular system is simply all the coefficients of the variables in the first 3 columns of the matrix, and the last column being the column of constant terms. Now, the coefficient matrix is obviously all the coefficients of the variables x, y, and z. So here, we will see that in column 1, we have all the coefficients of x being 1, negative 1, and 2. And column 2, here are simply the coefficients of y, which is negative 4, 3, and 0. And the last column being all coefficients of z, which is 3, negative 1, and 4. Now, what about elementary row operations? What are these elementary row operations? Now, there are 3 elementary row operation. One is that you can interchange two rows. Two, you can multiply a row by a non-zero constant. And three, you can add a multiple of a row to another row. Now, this is an example wherein we are going to apply the elementary row operation to solve a system of linear equation. Say we will have here a linear system which involves three equations in three unknowns, or that means to say we will have a 3 by 3 matrix, right? So what we need to do is to convert this linear system into an augmented matrix. So again, isolate all the coefficients of the unknown variables, and say for column 1, we will have the coefficients of x. You have 1, -1, and 2. And then column 2, which are simply the coefficients of y, -2, 3, and -5. And for the coefficients of z, we have 3, 0, and 5. So this is placed on the third column of the augmented matrix. And finally, the last column being the constant terms. So we have 9, -4, and 17. So just like how we did it last time with the row echelon form, what we want to do is to convert this linear system into a row echelon form. So recall, last time we simply added the equation 1 with equation 2, which forms a new second equation. And we also multiply row 1 with 2 and add that one with equation 3, so that we produce a new third equation. So here, while we operate it here on the left side, we can also apply the same thing with the right side. So here, if you're going to add equation 1, or say this is row 1, this is row 2, and this is row 3, say adding row 1 with row 2 to produce a new second row, we will have 0. So you have 1 plus -1 is 0. We have -2 plus 3 is 1. You have 3 plus 0 is 3. And then you have 9 plus -4 being 5. And we simply copy the first row as well as the third row since we did not change them. Now, the next step is, of course, we eliminate 2x. So by multiplying the first equation by -2 and adding it with equation 3, we will come up with the new third equation. So the same way with the right side, we are going to multiply row 1 by -2 and add it to row 3 so that we can come up with what happens here. So if we have -2 times 1 plus 2, this will be 0. Okay, now let's check on the next slide. So we will have here x minus 2y plus 3z equals 9, y plus 3z equals 5, and you have -y minus z is equal to -1. So when we multiply this by -2 and add it with elements of row 3, the last row would have entries such as 0. And if you have -2 here, so say we multiply this one by -2, okay? So you have -2 plus 2. Then the third row will be 0. So this will be 0 now. -2 times -2 is 4. 4 plus -5, that will be -1. So this is changed to -1. -2 times 3 is -6. -6 plus 5 will be -1. And we have -18 plus 17. That will be -1. Okay, so the third row is now 0, -1, -1, and -1. Now let us check on the next slide. Here, now see here that below 1 are all zeros. And taking note that 1 here is a coefficient of y. And we now need to make the entry here to be 0. Okay, so we're looking at the left side, we will have y plus negative. If we add equation 2 with equation 3, we form a new equation 3 that eliminates, wherein the negative y is already eliminated. So we will have y plus negative y, that becomes 0. And then we have 3z plus negative z will be 2z. So here we have 2z, and then we have 5 plus negative 1 is 4. And then we know we can already solve for z, which is equal to 2. And we apply back substitution. But here in our matrix, okay, we can simply add row 2 with row 3 to form new row 3. Okay, so that we will have 1 plus negative 1 will be 0. 3 plus negative 1 will be 2. And then you have 5 minus 1 will be equivalent to 4. This now will be your new third row. Now notice that we already have here the leading one, and below it are zeros. And then we have the next leading one, and below that one is also 0. Now we only need to convert 2 to 1 by saying multiplying row 3 by 1/2. So here, multiply the third row by 1/2 so that this becomes 1 and 2. So we can check it on the next slide. So we have here 1, 2, and then we apply your back substitution. So notice that in the augmented matrix, it is understood that all the entries in column 1 are the coefficients of x, and the entries in column 2 are the coefficients of y, and the entries in column 3 are the coefficients of z. And we also know that the last column are actually the constants. Okay, so what does referring to row 3, this simply means that 1 times z is equal to 2. Okay, and then according to row 2, that means 1 times y plus 3 times z is equivalent to 5. And then for row 1, that means we have x minus 2 times y plus 3 times z is equivalent to 9. So we simply apply our back substitution to find the value of x, y, which is x is equal to 1 and y is equivalent to negative 1. So for the elementary row operation, a matrix is said to be in row echelon form, or a matrix in row echelon form would have the following properties. Any rows consisting entirely of zeros occur at the bottom of the matrix. And for each row that does not contain or does not consist entirely of zeros, the first non-zero entry is called a leading one. And for 2 successive non-zero rows, the leading one in the higher row is farther to the left than the leading one in the lower row. Now, there is such a thing as row echelon form and a reduced row echelon form. Now, how do we differentiate a row echelon form from a reduced row echelon form? A matrix in row echelon form is in reduced row echelon form when every column that has leading one has zeros in every position above and below its leading one. Now, let us see some example here. So, the procedure for using Gaussian elimination with back substitution is summarized below. First, we write the augmented matrix of the system of linear equation, and then we use elementary row operation to rewrite the matrix in row echelon form, and we write the system of linear equations corresponding to the matrix in row echelon form and apply back substitution to find the solution, just like how we did it earlier. Okay, so we have another exercise here. So how do we solve the system using Gaussian elimination with back substitution?